Okay, welcome to CALOP's last seminar this year. Today's speaker is Myungeun Eom. She graduated from POSTECH, IME bachelor's degree in 2014.
2018 for
2018.
my undergrad. And
Okay, sorry. Yeah, 2018. Okay. Yeah, she entered 2014.
yeah.
2018 with the highest honor, and she got a master's degree from again the POSTECH IME department in 2020, right?
Yes.
And when she graduated, she published 2 first source papers and 2 course papers as a master's student. And then she started the PhD degree from 2021, right? 2021, and she'll be graduated in next May, hopefully.
Yeah.
Yeah, okay. And she had some experience on the Funo company, the AI image processing, and Amazon 2 times. And she'll give you a very interesting topic today. Okay, let's welcome her with a big applause.
Thank you very much for the nice introduction. Hi everyone, thank you for coming. It's an honor to come back to my alma mater to give a presentation. Today I'm excited to present my recent paper about dynamic non-bipartite matching. This is a joint work with my advisor, Dr. Alejandro Torriello. And if you have any questions or comments, please feel free to interrupt. Okay, I'd like to start with the definition of a non-bipartite matching problem. Just to remind you with some definitions, matching is a set of edges that do not share any common nodes. Here, the left figure, the set of red edges is an example of a valid matching because they do not share any nodes. But on the right figure, the set of red edges is not a matching anymore because node 3 is shared by edges 1, 3, and 3, 5. So this is the definition of a matching, and the matching problem is to find a matching, optimizing a given objective function. Here, objective functions vary. It could be to maximize the size of matching or to maximize the total reward in the matching. Here, we call the latter problem as max reward matching. And if you look at the title, what I mean by non-bipartite is I'm not making any assumptions about the graph structures. So on a given graph, any pair of nodes may be connected. And this is an example of a non-bipartite graph. In this presentation, I'll be talking about a non-bipartite matching where nodes arrive to the system dynamically. So it's a dynamic non-bipartite matching problem. And this problem was motivated by an application in freight transportation market. If you think about this market, shipment requests where an origin and a destination dynamically appear over time. Then a broker platform either assigns or auctions these requests to carriers, usually truck drivers. But one important thing to consider in this assignment is truck drivers want to avoid deadhead. Deadhead means driving without a paying load. So in the figure, let's say a driver ships a load from I to J and then returns to I without any other load. In that case, the red dashed arc will be the deadheading arc. And to reduce the system's over deadhead distance, the broker may pair or bundle requests. So for example, the ideal scenario for this one would be pairing this request from I to J with another request from J to I. In that case, the deadhead distance will be 0. And theoretically, we can bundle any number of requests Usually bundling many requests increases the operational complexity. So as a starting point, in this research, we restrict our attentions to only pairing 2 requests. Then we can model the situation as a dynamic non-bipartite matching. Let's consider 2 requests, one from O1 to D1 and the other from O2 to D2. Then we can compare 2 scenarios. The first one is each request is served by a driver who must go back to their origin. In that case, these red dashed arcs will be the dead heading arcs. But on the other hand, if you look at the right figure, if a single driver serves this request sequentially, departing from O1, going to D1, O2, D2, and then returning to O1. In that case, the yellow dashed arcs will be the dead heading arcs. So we can define the matching reward for this request pair as how much deadhead distance saved. In this example, it's going to be the difference between the length of red dashed arcs and the yellow dashed arcs. And with this reward structure, we can model this problem as a dynamic non-bipartite matching. And this model can be applied to other applications like a ride-sharing platform. I'll not go into details about this motivation, but again, we have 3 requests dynamically appearing over time. Then for a given 2 requests, we compare 2 scenarios. One, when a single driver serves this request as solo rides, so serve this request sequentially. In that case, the red dashed arc will be the total traveling distance. The second scenario is a driver serves this request as a shared ride. So the driver goes from O1 to O2, D2, and then D1. Then the yellow dashed arcs will be the total traveling distance. So for this application, we can define the matching reward as the traveling distance saved. All right, so with these motivations, now let me formally define the problem. We have a finite set of node types, N. Here you can think of each node type as the shipment request type or rider request type in ride sharing. So with origin and destination combination. And in this talk, we assume independent Bernoulli arrivals per period. So that means each node type I arrives to the system with probability Pi per period. And this Bernoulli arrival assumption is just for simplicity. In our full paper, we have an extended result for general arrival distributions. And next, we have a system parameter, sojourn period tau, which is a natural number. This means each arrived node remains in the system for at most tau periods. In other words, once a customer enters our system, we tell the customer the matching decision within this tau period. So we view this parameter as the maximum waiting time guarantee the platform provides to customers. And we have reward parameters Wij. So we assume the reward only depends on the node types. And we assume all rewards are non-negative. The objective is to maximize the long-run average reward. That is, we are assuming an infinite time horizon, and we want to find a policy which behaves well on average. Now, let me explain the system dynamics with an example. Let's assume we have 3 node types, I, J, and K, and tau is 3. In the middle gray circles are the nodes arrived to the system, and the numbers represent when they arrived. And now let's say we are at period 3. Then we can consider the nodes in the yellow background, nodes that arrived from period 1 to 3. And let's say we decided to execute this match. The matched pair immediately leaves the system, and we receive its corresponding reward. At the end of the period, nodes that have been waiting for tau periods, in this case 3 periods, leave the system without being matched. Next period, new nodes may arrive, and this procedure repeats. So far, any questions about the model? Yes?
The definition of the node is pair of origin and destination nodes in the previous article.
Yes, in the freight transportation or ride-sharing application, you can think of it as an origin and destination pair. And if you want to be more realistic, you can add the time component, so origin, destination, and pickup time. Any other questions? Or, yes?
잘 이해를 못한 것 같아가지고 한국말 되죠?
아,
예.
한국어로 해야지. 네, 그럼 한국어로 답변을 다시 하자면, 일단 이 모델에서 노드 타입들이 주어져 있다고 가정을 하고, 주어져 있는 노드 타입은 n이고, 각 노드 타입이 시스템에 어떠한 랜덤네스를 가지고 들어옵니다. 그래서 i의 경우에는 시스템의 pi의 확률로 발생을 하고 1 pi의 확률로 시스템에 발생하지 않습니다. 그래서 이렇게 다이나믹하게 랜덤하게 노드들이 발생하는 것이 하나의 상황이고, 이 서전 피리어드라는 말은 지금 타우가 3이라고 가정을 해서 설명을 하면 한 번 시스템에 도착한 노드는 총 3피리어드만큼 기다릴 수가 있습니다. 얘는 지금 이 넘버들은 어느 피리어드에 도착한 노드인지를 의미하는데, 얘는 피리어드 1에 도착한 타입 J 노드인 거고요. 얘는 피리어드 3이 되면 매칭되지 않았다고 해도 시스템을 떠납니다. 왜냐면 이 타우 피리어드 때문에. 그래서 이 환경에서 목적은 평균적으로 타임 호라이즌을 계속 이렇게 진행하는 상황인데, 평균을 냈을 때 그 리워드가 크게 할 수 있는 펄스를 세우는 것이 목적입니다. 네. Any other questions?
Does the arrival distribution have to be same for all nodes?
So the arrival, we assume each node type arrives to the system following independent distribution. So type I has arrival probability Pi, type J has arrival probability Pj. But each node type follows the same distribution. That's our assumption.
By matching, what do you mean in this case?
In this case, in my system, I have many nodes. Each node has its node type and when it arrived.
So in the case,
Yes,
node
I'm
type
matching.
K arrived in time period 2,
Yes.
and then 3 arrived in
I
node type
arrived
I.
in 3. Yes.
Then how do you match I and K?
So in the ride-sharing application, so if you think about of this node type as a ride request, going from, let's say, POSTECH to Pohang Station, POSTECH to Idong, I'm matching these two requests. That means I'm forming a shared ride. So these two riders will share one taxi.
Okay. And matching provides the reward.
Yes, yes. Okay. So this is a dynamic non-bipartite matching problem. And a natural question to ask is, can we find an optimal policy, right? So for that, we started from some simple policies, batching and greedy policies. Here, roughly speaking, batching policy accumulates a batch of arriving nodes within a fixed period, and then optimizes matches over each batch. And greedy policy is similar, but it makes matching decisions as opportunities arise by optimizing over available nodes at the moment. I'll explain about these policies later. But these policies are known to be very good, very appealing in practice because they tend to perform very well. And also they are easy to implement. Then another follow-up question is, are they really good theoretically? If so, how good are they? But surprisingly, in spite of their prevalence, there have been a limited number of studies analyzing their theoretical performance. And these 5 are the most relevant papers. I'll briefly explain their models and main results. For arrival distribution, they assume Poisson processes, adversarial arrival, and multinomial distributions. And for the sojourn time, except for the second paper, they assumed exponential, 0, or infinite sojourn times. But their assumptions do not align with our definition of the sojourn time because we consider sojourn time as the maximum waiting time guarantee, so it has to be a finite number. And this paper, which considered the fixed sojourn time, they developed algorithms with constant competitive ratios. But our goal is we want to understand how the performance of these policies changes as the sojourn time grows. So we want to understand its asymptotic behavior. So before presenting our main results, now let me formally define the policies we're going to analyze. First, the batching policy solves a max-word matching, executes all the matches, and clears out the system every tau periods. Your tau is our sojourn time, and we use it as a batching interval. For example, when tau is 5, we wait until period 5. At this time point, we solve the max-word matching, considering the nodes in the yellow background, and execute all the matches and clear out the system. And we wait until period 10, solve the matching, and repeat this procedure. So this was about the batching policy, and for greedy, it solves the max-word matching, executes all the matches every period. So now let's assume we're at period 5. Now there is nothing to match, so we go to the next period. Next period, new nodes arrived. We solve the max-word matching. This is the optimal solution, so we execute this match. Then this procedure continues. These policies are very simple, simple and straightforward, which is good in practice. But unfortunately, the greedy policy that I just described is not optimal. It may perform significantly worse than the optimal. And there exists a very simple instance. Suppose we have 3 node types, I, j, and k, and tau is 3. So assume the rewards for JK pair is very large, but other rewards are very small. Then intuitively, it is optimal to match only JK pairs, so ignoring the existence of type I nodes. But then let's make the problem more tricky. Suppose the arrival probabilities of type J and K are smaller than that of type I node. Then we may encounter a situation like this. In the system, we have a lot of type I nodes, but a few number of type J or K nodes. And at period 3, if you recall the greedy policy, it will solve the max-word matching problem considering the nodes in the system. Then this is the optimal matching solution. We have only one choice. So the greedy policy will execute this match and receive the reward of 1. But actually, this is a bad match because we could have waited for next period and used this J node to match with type K node and receive a much higher reward. This situation happens even if tau goes to infinity. So the simple greedy policy doesn't work. And this happens because the greedy policy doesn't care about the future at all. And to prevent from the greedy policy making bad matches, we propose a modified greedy using reserve price. To formally define the modified greedy, it solves the max weird matching problem with reserve price, and then executes matches including expiring nodes every period. So what I mean by the reserve price is, this is the same example from the previous slide. For each node in the system, we compute its reserve price. Informally, this is the expected future reward we can receive by reserving this node for the future. After computing this price, we create a dummy node for each node and set the reward of dummy edge to its corresponding reserve price. And considering these dummy edges in addition to the original edges, we solve the max weird matching problem. So the dummy edges have reserve price as a reward, and original edges has the original reward. After solving the problem, let's say this is the optimal solution. The yellow glowing edges is the optimal matching solution. Then because only dummy edges are selected, we do not execute anything. So even if there exists an original edge, by using this reserve price, modified greedy will not make this bad match. And of course, depending on parameters, this might be the optimal solution to the same graph. Probably, for example, when the reward for ij pair is very large, then this would be the optimal solution. In this situation, the original edge is selected. That means we execute this yellow glowing solid line. The point here is, by using this reserve price, our modified greedy makes optimized decisions considering the future. Before moving on, any questions about the policies? Yes?
Could you explain again about the definition of the reserve price here?
Yes. Actually, I haven't explained the definition. The informal definition is the expected future reward we can receive by saving this node for the future. So if we match this one node, then we receive immediate reward. But if we reserve this node for the future, then there should be something expected future reward. And I'm calling that an estimate of the future reward as reserve price.
So there's a certain way to calculate the reserve price.
Yes. Yes, I'll explain later. We define this reserve price based on driver distributions and the reward. Yes. Yes.
If you don't match some node this time, then there won't be a chance of arriving new.
Yes. So that depends on each node's remaining period. So for example, this node, let's say tau is 3. Then this node, which arrived in period 1, will leave the system next period. So if we do not use this one, it will disappear. But this node, it still has remaining periods of 2 periods. So next day, we still have a chance to use this one. And when we compute our reserve price, we use that remaining period information. Did I answer to your question?
In my thought, like if you match the node I and node I at period 1,
Yes.
then there will be a new chance of new node I to arrive at period 2.
So you're assuming we're at period 1, is that right?
Yes. So
Yes.
if I match the node I at period 1, then it would disappear in the system.
Yes, right.
So there will be a new chance of new node I to come in at period 2.
Yes.
So if we don't match at period 1, we would lose a chance of matching a new node. So,
I think you're talking about this node, right?
yes.
If we match this node at period 1, the match node disappears, so we cannot use it next period. But if we do not match this one, we keep this one, and we can use it at the next period.
Yes, so my question is, I'm sorry, does the reserve price consider some kind of like expectation of?
Yes, reserve price considers how many periods are remain for each node.
Thank you.
Yeah. So if a node has lots of remaining, many days of remaining periods, then its reserve price will be higher. Yes.
Thank you.
Thank you. Okay. Any other questions? All right. So I explained the batching and modified priority policies, and our main results are we showed the asymptotic optimality of the batching and modified priority policies. Here, H tau denotes the average reward of policy H with sojourn tau, and B is for batching, and MG is for modified priority. As you can see from these two rows, batching and modified priority converge to the optimal as the sojourn time increases. And here the convergence rates are 1 over square root of tau for batching and 1 over tau for modified priority. And more interestingly, we showed they converge exponentially fast to 1 minus epsilon optimality. This implies by sacrificing the optimality a little bit, we can make them converge exponentially fast. And this can be very useful in practice. In addition, we have instances where the convergence rates are tight. That means we cannot do better than 1 over square root of tau and 1 over tau for our batching and modified priority policies. The only assumption we needed to derive these results is bounded support for arrivals. Right, then I'll use the remaining time to describe how I derived these results. Here, basically, we want to understand, analyze the difference between optimal solution and batching or modified priority solutions. But we don't know what the optimal solution is, so we needed some kind of a benchmark. For that, we developed a fluid linear programming relaxation model. This fluid model relaxation is one of the techniques used for a Markov decision process. So the intuition is we relax the integrality constraints and consider we have a fluid amount of arrivals per period. In our problem, we assume we have this pi amount of arrivals per period for each type. So the model is we have a decision variable Zij representing the average matching frequency of a pair. And the objective function is we maximize the average reward. And the only constraint is we cannot match more than what we have. So the sum of matching frequencies should not exceed the expected arrivals per period. So this is a valid relaxation model. We can formulate our problem as an MDP, and taking expectations, aggregating variables, we can derive this relaxation model. So this one gives an upper bound on our problem. And we use this model as a benchmark and analyze the difference between the optimal fluid LP solution and batching modified priority solutions. Here, the model is very simple, but still analyzing these differences are not that straightforward. So we started from the simplest case. Let's say, let's assume we have only 2 types in the system, I and J. Then the pair IJ is the only available batch. And if you go back to this model, if we have only two types, we have two constraints. Zij is less than or equal to Pi, Zij is less than or equal to Pj. So the optimal fluid LP solution becomes the minimum between Pi and Pj. So for a single pair case, we know the optimal fluid LP solution. And also we have we have an equation for the average matching frequency under the matching policy. Here AI denotes the number of type I arrivals in tau periods. Tau is our matching interval. And because we're assuming Bernoulli arrivals, AI will follow the binomial distribution with parameters tau and Pi. And the number of matches we make in matching intervals is the expectation of minimum between AI and AJ. And we divide that term by tau and get the matching frequency. And using concentration inequalities like Markov inequality, Hoeffding's inequalities, we can show the equalities here. The terms on the right-hand side. Oh, sorry. Yes, the terms on the right-hand side. If the arrival probabilities are identical, then the convergence rate, we get slow convergence, 1 over square root of tau. If not, we get exponential convergence, as you can see from the second row. And this exponential convergence implies the exponential convergence to 1 minus epsilon optimality. If you look at the third bullet point, if Pi is less than 1 minus epsilon times Pj, then by plugging in these parameters, we get the exponential convergence like this. But even if not, we can randomly discard type I arrivals so that the adjusted probability satisfies this condition. So in conclusion here, the matching policy converges to the optimal as the sojourn time increases with those rates for a single pair case. And for greedy, we analyze the difference between the optimal fluid LP and optimal fluid LP and the matching frequency under the greedy policy. If we apply the greedy policy, we can describe our system as a discrete time Markov chain. We show some properties of this discrete time Markov chain and managed to derive a closed form equation for the unique stationary distribution. And using the stationary distribution, we derived the equalities here. The difference between optimal fluid LP and the greedy matching frequency. The terms are very messy, but if the arrival probabilities are identical, then we get the convergence rate of 1 over tau. If not, we get exponential convergence. And again, the second term in the orange box implies exponential convergence to 1 minus epsilon optimality. So these were about a single pair. Then the question is, can we extend these results to a general setting? To handle the general problem, we followed 3 steps. First, we defined randomized batching and greedy policies. And then we showed those randomized policies have the same convergence rates as in single pair cases. Last, we show the dominance of batching and modified greedy over their randomized counterpart. Oh, so for any questions? Yes?
Is there any chance to improve the result by considering modified batching?
That's a really great point. So my batching uses the batching interval tau, which is the same as sojourn period. If we use optimized batching interval, there's a chance we can do better. But I don't have any results about modified batching. All right, so let's go back to this randomized policies. For this randomization, we use the optimal fluid LP solution. Recall that this is our fluid LP. Given the optimal solution Z star, we define normalized value Z bar. And we use the Z bar values when when assigning subtypes. Here we introduce the concept of subtype here. Let's look at an example. At period 1, let's say we have new arrivals, one type I and one type J. And we assign each node to subtype, so each type I node to subtype ij with probability Z bar ij. So here the letters written in the circles define the subtypes. This one has subtype ik, and the second node has subtype ji. So we randomly assign these subtypes using the normalized values here. So this continues, and all the nodes in our system will have their assigned subtypes. With these subtypes, we add a restriction that randomized policies consider only node pairs whose subtypes match. So in this example, the blue line is a valid match because their subtypes match as ij and ji. But the red dashed line is not a valid match anymore because their subtypes do not match. This one has ik and the lower one has kj. And with these restrictions, randomized policies decompose the general problem into multiple independent single pair cases. The problem system, the previous system will be decomposed into 3 independent single pair systems. One for ij, ji subtype pair, ik, ki subtype pair, and jk, kj subtype pair. And because these single pair systems are independent, the optimality gap of randomized policies for the general problem is simply the summation of optimality gaps for single pair cases. And because of this independence, the convergence rates for single pair cases are inherited into the general problem. So here the conclusion is randomized policies have the same convergence rates as in single pair cases. And the remaining part, yes?
Yes. Could you explain why in period 1 and 3 they have different subtypes K and J? I don't understand. They are determined by the solving AP.
Yes.
I think the solution should be same because they share I. So for I in period 1,
Yes.
subtype is IK.
Yes.
But in period 3, the subtype is IJ. So why they are different? I don't understand.
So depending on the system parameters, there may exist a solution where here ik star and zij star are both positive. That we are defining the z bar by normalizing this z star. So in that situation, z bar ik and z bar ij will both be positive. And because we are assigning this subtype randomly, yes, because of the probability, the positive probability, these two nodes may have different subtypes. Yes, thank you. So the remaining part is we need to compare the batching and modified greedy policies with randomized policies. First, for batching. Batching and randomized policies both execute matches and clear out the system every tau periods, for every batch. That means batches are independent of each other, and it is enough to compare the solution for an arbitrary batch of an arbitrary sample path. And for a given batch, the randomized batching solution is a feasible solution to that batch's max weird matching problem. And because the batching policy uses the optimal solution, batching is always better than or equal to the randomized batching. And for modified greedy, here I explained how we design reserve price. Consider a node with subtype ij and remaining period r. So we have r, periods of remaining times. And if we decided to reserve this node for the future, that means we are kind of expecting the chance of using this node to match with subtype ji node arriving in the future, arriving in the next r-1 periods, because this one will leave the system after r periods. So if such node appears in the system, then we can get the reward of wij by matching these pairs. Based on that, we defined its reserve price as wij times the probability subtype ji node arrives within next r-1 period. And using this reserve price construction and Bellman equation, we can show the dominance of modified greedy over the randomized greedy. And this concludes the asymptotic optimality of batching and modified greedy, and also their convergence rates as in single pair cases. Any questions about the reserve price? Okay. Yes?
The reserve price is just one for each node. You
Yeah.
can consider multiple upcoming node.
Yes. So this is just, I would say this is a lower bound of the future expected reward we can expect. If we can consider multiple nodes, not only just J, other types, then probably we can get better reserve price. But that analysis was too complicated, so I ended up using only 2 types. And we compute this reserve price for all nodes in the system every period. And because this one, the reserve price depends on the remaining period, we update this reserve price every period. Right, so far we showed this theoretical performance of these policies, and to evaluate the empirical performance, we designed the ride-sharing marketplace instance. Based on taxi data from New York City Open Data, we designed the simulation environment. And as I explained in the motivation, we defined the matching reward as the traveling miles saved. And we compared 4 policies. First one is myopic, which is the straightforward greedy that is not optimal, that may perform significantly worse than the optimal. And we tested modified gradient batching and an offline policy. Here, the offline policy solves the max weird matching for the entire time horizon, assuming we know all the arrivals in advance. So this is another benchmark different from the fluid LP. And we used 360 periods of time horizon and compared 5 different sojourn times, from 6 to 18. And this is the result. The left figure shows the average reward obtained by each policy for different sojourn times. The black dashed line is the fluid LP bound. As you can see from the green and orange colors, batching and modified greedy objectives approach the LP bound as the sojourn time increases. This aligns with our theoretical findings. And surprisingly, when the sojourn period was only 18, they already achieved around 96% of convergence. So this means for this instance, batching and modified greedy perform very well with reasonably small sojourn time. And the right figure compares the average waiting time obtained by each policy. So even though this was not our objective function, this is an important secondary factor. So we compare this value, and average waiting time of batching was significantly less than that of modified greedy. So in this application, the system manager would prefer to use the batching policy. So in conclusion, we showed the asymptotic optimality of batching and greedy policies. The interesting part was the exponential convergence to approximate optimality. And we have some interesting extensions. In this talk, I didn't explicitly mention, but I was assuming same time matches were not allowed. But indeed, we can extend our results to a setting where same type matches are allowed. And if same type matches are preferred, then batching and modified greedy show much faster convergence. 1/tau for batching and exponential convergence for modified greedy. And this is relevant to a ride-sharing application because in ride-sharing platform, the ideal scenario is to match two riders with the exact same origin and destination pairs. So probably this is why in our computational study, batching and modified greedy were performing very well. And we also extended our result to a setting where impatient nodes exist. In this setting, we assume unmatched node I may abandon the system with probability di tau in its period. Here we are assuming the departure probability is a function of the sojourn time. If these assumptions, departure probabilities satisfy certain conditions, then our batching and randomized greedy are still asymptotically optimal. Roughly speaking, if the departure probability decreases as the sojourn time increases, then batching and randomized greedy are still good. But if there is a stronger node impatience, then there exist instances where batching is not asymptotically optimal anymore. This is not surprising because our batching interval was the same as the sojourn time. But if there is a stronger node impatience, then probably many nodes will leave before reaching the sojourn time limit. So using optimized batching interval would be required to handle this case. And even with stronger node impatience, there exist instances where randomized greedy does not converge to fluid LP objective. This means our relaxation model is too weak. Again, this is not that surprising because our fluid LP doesn't rely on the departure probabilities. So to handle these cases, we need a stronger relaxation model, and I'm currently working on this direction. And I'd like to conclude this presentation with some comparisons between batching and greedy policies. So I introduced various policies: batching, randomized greedy, and modified greedy. And one of our questions while we were doing this research was, is there any clear dominance? Which one is the best? And the conclusion is there is no clear dominance. At least empirically, we found instances where batching is better or where the modified greedy is better. But still, we found some trade-offs. For example, the matching policy we're using is oblivious to distributions. It does not use arrival distributions or anything. But instead, it is more vulnerable to node impatience. On the other hand, the randomized greedy requires expectations because we solve the fluid LP, and the fluid LP uses that expectation. But using this expectation, it allows more impatience and it shows better asymptotic performance. We can also compare the randomized greedy with modified greedy. As I said, randomized greedy requires only expectations, but the modified greedy requires distributions because when computing the reserve price, we used the distribution. But using this fine information, it shows better empirical performance. And this trade-off is very subtle because usually estimating distributions is much more difficult than estimating expectations. So this gives us another interesting question. Well, what if we learn from the data instead of assuming a known stochastic distribution? And there are lots of other interesting questions related to this problem. And if you're interested in, please check out our paper, which is available online. Thank you very much.